Welcome to the class. This is an introduction to some basic concepts for our class. Let's first talk about the atmosphere, and remember that when we talk about the atmosphere in this course, it refers to that column of air that's above a specific area. It's kind of mind-boggling to me to think of a person, and then here you have the atmosphere on top. So we're talking that the air above us creates pressure on our heads. So it applies a specific pressure, and this is the composition of the atmosphere. So it's not all oxygen, only 20 to 21% is oxygen. Most of it is nitrogen. We have argon, carbon dioxide, and other traces of other gases. One atmosphere refers to the atmospheric pressure, and I just want to show here some units that are very important. Whenever we refer to 1 atmosphere, it's also 1.014 times 10 to the 5 newtons per square meters, or those are pascals. 1.014 bars, or 14.7. So this number is important to remember, because we'll talk in this class a lot about pounds per square inch, or 760 millimeters of mercury, or 10.33 meters of water. So if you remember partial pressures from prior courses, if you have 1 atmosphere, the partial pressure of oxygen is going to be 1 atmosphere times its percentage, which is 0.295%. So the partial pressure of oxygen in 1 atmosphere would be 0.209 or 0.21 atmospheres. For nitrogen, same thing, it's 0.78 atmospheres. So this is an important concept that you'll be it'll come back with other classes. You also have learned about when a substance changes a phase from a solid to a liquid, from a liquid to a gas. Now in this class, whenever we refer to water, the default is liquid water. Okay? So as you move from one phase to another, you have to add heat. And in turn, the heat added turns into heat absorbed, right? And you know that because whenever you put water to boil in your stove, if you put it at a low, it'll take a long time. So you're not adding as much heat, but if you put it really high, you're adding a lot of heat. So whenever we talk solid in water, we're referring to ice, of course. Then you have to add heat. But whenever you add heat, remember that it doesn't automatically turn into liquid. So let's think about a cooler. And a cooler you have you haven't used this in a long time, right? Because you haven't been out in a tailgate. But whenever you have ice in the cooler, the ice starts to melt. But not all of the ice turns liquid. So it's sort of like in this phase here. So you have a mixture, solid, liquid, ice and water in this case. Until all of the ice is melted, the temperature will not increase in that cooler. So once you have all liquid, then you can see an increase in temperature, and the same thing whenever you are boiling water. So as you have boiling water, you have the water increases in temperature and some of it starts to evaporate, but not all of it. If I were to put a thermometer here, what I would see is that when the water starts to boil, I have, if I am at 1 atmosphere of pressure at 100 degrees Celsius, the water will boil. But it doesn't matter if I keep adding heat, it won't go past 100 degrees Celsius. So here, if you have 1 atmosphere of pressure, then this temperature here, of course, 0 and, and here would be 100, okay? So once all the water is in the gas phase, that's when all of the water has melted. But at this point, whenever you have this boiling water, at this point you have a mixture of liquid and gas. There's going to be some questions here, so answer them in the Juja quiz. So let's talk about the vapor pressure. Vapor pressure is the pressure exerted by water in the water vapor phase in the atmosphere. When vapor pressure equals atmospheric pressure, that's when boiling takes place. And this is really interesting because if you see atmospheric pressure as if it was a piston, the same concept. So you have, let's say that this is the atmosphere, right? Remember the piston. So what happens is, if I have water here, right, the water will start to evaporate and there's some vapor, but not all of it will vaporize until the vapor pressure equals the atmospheric pressure. So if I have 1 atmosphere of pressure, I have 100 degrees Celsius that water will start vaporizing. But at that point, this is what happens. Now, let's say that I have a pressure cooker. What does the pressure cooker do? Well, a pressure cooker, what it does is, it's going to increase that pressure and it's going to be larger than 1 atmosphere. As a consequence of this, I'm pushing down on this vapor that it's formed here on top of the water. Okay? I'm not a very good draftsperson, but just I want you to visualize this, that with the pressure cooker, what you're doing is pushing down on this vapor pressure. So you're not letting the water vaporize at 1 atmosphere. So what will happen is that here the water will vaporize at a temperature that's larger, at a pressure that is larger than 100 degrees Celsius. So that's why you can reach higher temperatures, because you are not allowing, in this case, you have vapor pressure has to be equal to the pressure cooker. Okay, so you have if you have an instant pot, for example, same concept, what you're doing is really increasing the pressure on top of that water, so that in order for the water to boil, 2 things have to happen, right? The pressure in the water has to overcome that pressure from the pressure cooker, and so the result of that is that you can maintain a temperature in the water that's higher than 100 degrees Celsius. So a very important concept: as you increase the temperature, or as you increase the pressure, you increase the boiling temperature. So at 1 atmosphere, boiling takes place at 100 degrees Celsius. elevation for El Paso is 3,740 feet. So one thing that happens is that as you increase in elevation, the atmospheric pressure decreases. Now this makes sense because if I am here at sea level, I'm here by the ocean on the shore, right? I have this much column of air above me, and then now I am in the mountains. So you can see that as I increased in elevation, there is less pressure on me. So the atmospheric pressure is reduced. The concept of partial pressures remains the same. So I still have in 1 atmosphere pressure 0.2 atmospheres of oxygen. But now if I have, instead of 1 atmosphere, if I have 1 atmosphere of pressure times 0.2, right? Now if I am an elevation that, for example, at in El Paso, so I have less than 1 atmosphere times the 0.2 is going to be, the concentration of oxygen is going to be much less. So this relationship gives you the altitude or elevation with atmospheric pressure. So then again you can see this concept in a graph format. Okay. So 1 atmosphere of pressure is 14 pounds per square inch, or 101.4 kilopascals. Let me so let me erase. I apologize for that. So atmospheric pressure in El Paso, we have 0.87 atmospheres. Okay. So lower atmospheric pressure, lower temperature for boiling. Again, the same concept of the pressure on top of the water. If I increase the pressure, the boiling temperature increases, but if I decrease the pressure, the boiling temperature decreases. So let me give you an example. I'm from Puerto Rico at sea level. So the hardest thing for me was to learn to cook rice when I came to El Paso. I was burning the rice over and over because since the boiling temperature is lower, I was running out of water in my rice faster or earlier than in Puerto Rico. So I had to learn to make rice by adding more water to my rice. So the water boils here at 96.27 degrees Celsius. Okay, so these concepts are really important. Just look and understand the relationship between pressure and temperature. Pressure cookers increase gauge pressure. So the gauge pressure is the pressure above atmospheric pressure. Okay, so whenever you have a gauge in a tank or something like that, what you're measuring is gauge pressure, because you want to make sure that the pressure is constant no matter what elevation you have. So this is really important. So this is why if you have gauge pressure of 0, this has 100 degrees Celsius, because you are not adding any extra pressure above atmospheric pressure, and you can see all of this. Okay. So this is the concept of the pressure cooker. The great thing about this video is you can pause and understand the concepts. Okay. one thing you've seen is how in the wintertime you add salt on the road, and a mixture of salt and sand. Sand will increase traction, but also adding salt does that. But in addition, it will, if you add here the salt, what it will do is it will decrease the freezing point. So what will happen is that if you normally have at 0 degrees Celsius, you have freezing. By adding salt, it decreases it even more, so that then you'll have liquid or water instead of ice. One of the things that happens, and I want to encourage you to do this kind of experiments whenever you cook. So if I have boiling water and add salt, what happens to the boiling point? Also that changes, and you can see that you had boiling water, you add salt, and for a moment it'll stop boiling as well. So it'll also increase the boiling point. So one thing important is the density of water. You know, we usually say, oh, it's 1 gram per cubic centimeter, but in reality it's less than that. And within this range, you can see how the density is decreasing. And although this is a long range of temperatures, one of the things I wanted to point out was between this range of temperature, you have a change in the density of water. For most practical purposes, we'll always assume a density of 1 gram per cubic centimeter or 1,000 kilograms per cubic meters, unless I indicate differently or the problem indicates differently. So if you have you are giving a temperature, then you go to the FE manual and find what would be the density for that specific temperature. In hydraulic applications, in civil engineering, we usually assume 1, but what happens is that when you have temperature changes, you have to take that into account. So one of the things we'll talk about is viscosity of water, and think of viscosity as more viscous or less viscous. Like honey is very viscous, but then water is less viscous than water. So it has to do with how fast the water moves between 2 plates, or the liquid moves between 2 plates. So just think of that friction and that force that you need to move a plate of that or imaginary plate of that liquid. Okay, so that's the shear stress, and viscosity of water is related to the shear stress. Look in your book the definitions of the shear stress and tension or shear stress over area, or the force over the area. And so the mu is the absolute viscosity, and the nu is the kinematic viscosity. And this is really important, and they are related by the density, as you can see. And one of the things is that if I give you a value of viscosity, you look at the FE manual and look at the properties of water, and you will know which units, the units tell you if it's absolute or kinematic viscosity. Okay, so if you have Poise here, or Newton seconds per square meter versus square centimeters per second, or Stokes, then you have absolute versus kinematic, and this is very important. This is the table that gives you the viscosities, and you can see here which viscosity is absolute or kinematic. Surface tension is really the force that pulls the water together due to attraction forces between the molecules. That's what makes a drop exist. And you can see that that is the shape of drops, and this is due to surface tension. Liquid has neutral attraction, so this is very important concept. Also, that is what prevents a mosquito from drowning. And so whenever you overcome the surface tension, that's when you sink. So this paper clip here, if I put it like this, right, it'll sink because I am increasing the pressure, and because pressure is the force divided by area, or the weight divided by area, but here you have the pressure evenly distributed in such a way that it's less than the surface tension. It does not overcome the surface tension. Remember statics and how in order to exist some movement, right, you have to overcome the forces. But if the sum of the forces equals 0, then you don't have any acceleration. Okay. So the units are newtons per meter usually. So we have what it's called the surface energy, which is Newton meters per square meter. What does soap do, right? Soap reduces the surface tension of water. So if you have a mosquito, like you have in this, but if I added soap in the water, you'll see the mosquitoes sink, okay? Because the surface tension is reduced, okay? One thing that I want to point out, how here you have the surface tension. Well, let's look at this. 0.0073 and gasoline 0.022. So gasoline spreads more than water. The surface tension in water is stronger than gasoline. So this is really important. So and at different temperatures, that surface tension changes. Okay. So the soap reduces the surface tension dramatically, as you can see. So you can see this here. So you have some links to some videos. I encourage you to watch those. Surface tension also is partly responsible for that capillary effect. And what you will see is the capillary action is occurs because water molecules bond to each other, so they tend to attract. And so what happens is that there is also water that adheres to a material, and it will cause an upward force on the liquid, and it's the capillary action. This is super important, especially in groundwater, because whenever you have groundwater, there's capillary action, and the water that it's within the capillaries in the soil, it's not so easy to extract. And so this is important concept for our future discussions as well. So the height of the capillary action will depend on the size of the tube. So the thinner the tube, the higher that column of the liquid it will be. And again, you know, if you have water, it'll go a lot higher. And it will be limited by gravity, of course. So capillary rising is inversely proportional to the radius of the tube and the density of the liquid. That's a very important concept. So one of the things is the capillary effect will depend on the liquid. So if you have water, it's a wetting liquid, and you'll have the meniscus, and you learned this in chemistry. But if you have mercury, it's a non-wetting liquid, so this angle will be a lot larger. And so there's equations that you can use to determine what is the height based on that angle. We're not going to go into details, and there might be one or two problems in the book for that, but it's a straightforward application of the